Hello everyone, thank you very much for joining me again in regards to the maintenance and repair of this Marconi 6200a microwave test set, which is identical to the one I use, my operational one, which I've fed to this monitor so we can see things easily. As in part 2, what I've done, because the fault with this test set is that the RF level coming out to the front socket which connects here is incorrect in comparison to what it should be, and in addition it won't self-calibrate the RF level as well, which is a fault which I'm going to go into shortly. When I show you in the next part what happens is we've removed what is the diode attenuator and the pulse modulator from the microwave chassis, which is this section here, and as an experiment what we're doing is we're feeding in a swept frequency from 10 megahertz to 19.9 gigahertz in here at 0 dBm, and then we're measuring the RF coming out on the scalar detector. So this is basically what we're getting on the scalar, the performance. So we've got a start frequency of 10 megahertz, a stop frequency of 19.9 gigahertz. One of the interesting things to note is, although the response is a little bit wavy as we go up to 19, some of this is down to the cable I'm using. The cable I'm using is only really good up to about 10 gigahertz really. Beyond that it starts getting a bit lossy, so that's equates for some of what we're seeing here. But I just wanted to show the full frequency spectrum really of the test set and the performance that it should give. What I can see straight away, even before we apply any voltages to what I think is the pin diode attenuator, is we've got a minus 5.17 dBm loss already. So even without this attenuator being fed any voltage to control the attenuation or current, that it's still got a 5 dB loss across it, which I do find quite strange. But anyway, it's relatively flat really across the frequency bands. I mean, if I put the markers on, and if we adjust the marker and keep an eye on the level, you know, I mean right down here we go right to the beginning, which is 10 megs, we've got just under 5 dB loss with 0 dBm in, and then if we go right up to 19.9 gigs, it's 7 dB loss, so it's only a couple of dB difference really from 10 megs to nearly 20 gigahertz, which isn't bad, on the grand scheme of things, considering the cable losses and things like that have to be taken account of. So what I'm going to do is I'm just going to show what happens when we adjust the current. Now what we've done is we've connected supply leads here, and we've set a current limit on the power supply to 100 milliamps, and obviously then we're not going to blow this up if something goes wrong. We're not going to dump loads of current into it and burn it out. So let's just have a look at what happens when we adjust the DC voltage. So if I start very minutely, so we're in the order of hundreds of millivolts instead of volts, we can see straight away, oh blimey, that's less than 1.7 volts, that's 7 milliamps, 70 milliamps. So now we're at 2.7 volts at 100 milliamps, and that's 3.4 volts at current limiting now at 130 milliamps. So as you can see, it's doing a good job of attenuating across that frequency band. Now if we start to reduce the voltage again very gradually, that's 2 volts now, and we can see it's starting to come back. Now I've been quite careful with the current limit because I didn't want to damage it, and now that's 0 volts, so it's acting more of a current device rather than a voltage device. There's a little bit of voltage obviously getting to it, but it's mainly the current. I've set the current limit, and it is current limiting at just over 100 milliamps. So I think that proves really that it's working insofar as attenuation with proportional to DC voltage. Now what I did, I reverse polarised the supply voltage to it just to see whether it does anything different when it's getting a minus volts supply, and it didn't do anything at all. So obviously it's just a positive voltage that's applied to it from 0 up to whatever. So that is obviously interesting. But what I have noticed as well, when I increased the current earlier, when the attenuation was on, this part here, which is a low frequencies, when there's more current applied in the flow in the circuit, that flattens out more. So I think it just needs more current, but because I don't know what its spec is with regards to supply, I'm not going to try and blow it, you know. So, but I think that demonstrates pretty well. And of course the DAC voltages then just change ever so slightly with just millivolts difference between them, or the current drive, just to adjust attenuation up and down. So I'm going to do an experiment, I think, at some point with the modulation running. Let's have a look, see if I can get this to focus in a bit more. But the diagram, I've got a functional description here that I got out the manual, and this is the diagram. So this section here is what we were looking at. That was a coupler, if you remember, in the last part of the video, which is that thing there. This is a coupler, which then connects obviously to the bits that we've got out already, the attenuator, and then here we've got, which is the pulse diode detector, according to that. So that's that other unit, that other module, which I believe to be this thing, because that connected to the coupler, that I believe is a diode detector, and this then is the what appears to be the attenuator or modulator. That's an attenuator as well. But I think, if anything, this is a rectifier diode. There's no way, obviously, high frequency 20 gigahertz can be down that cable. It's just simply not the right kind of cable for that frequency range. It'd probably be a rigid coaxial cable if that were the case. So I believe that what this is rather than being a signal input to modulate the carrier, which it could be as well. I mean, I don't know yet. I'll read the functional description. But this here gives a signal, appears to give a signal to this and rectifies it, and then a DC voltage is fed out as part of that. I don't know. I doubt it myself, but it could be that the modulation's done in the pin switch assembly instead. It's very confusing, and you'll understand that in a moment when I read it out. But if we just go back to this part of the circuit, that's the might get the damn thing to stop moving about. So that's what is the attenuator module, and we're currently feeding a signal in here on this port, and then I have the scalar detector fitted here, and then we're adjusting the voltage, which is this ALC line here. This is a leveling amp, which is in the synthesizer, and that's the synthesizer we were looking at in the previous video on part 1. But what we can see with this experiment is that by giving a small control voltage here, adjust this attenuator within it. So this seems to be working. So I don't think the fault lay there. I think it lays either in the digital board or in the synthesizer board, not able to control the DC voltage, the level inside. Now, one of the interesting things about this is that it doesn't call it an attenuator there, it calls it a, well, it is a pin diode modulator, pick-off, not an attenuator it refers to. So in the functional description it says here, the microwave chassis is responsible for signal generation above 2 GHz by means of one or more Yig-tuned oscillators. The number of Yig-tuned oscillators depends on the instrument version. 1 for the 6201, 3 for the 6200A, which is this instrument, and 4 for the 6203 and 6204 models. The 8 to 12 GHz, 12 to 20 GHz oscillators are followed by discrete low-pass filters to reduce harmonics. So that is those two there that we can see, and then it goes on to say the 2 to 8 GHz oscillators contains an integral tracking filter. A pin switch for the 6200, which is an SP4T, selects one of its inputs. So again, that's that module, that's a pin switch. And then what happens is it says, which includes a 10 MHz to 2 GHz signal generated by the synthesizer block. A broadband directional coupler separates out part of the signal from the tune oscillators, i.e. frequencies above 2 GHz, which are sampled by the sampling gate mixer and used for phase locking as described earlier. So that's that unit there, that's a sampler. Then it says a broadband directional coupler separates out part of the signal from the tune oscillators, frequencies above 2 GHz. The through path of the coupler is followed by a broadband modulator, which together with a resistive pick-off coupler, diode detector and control circuitry in the synthesizer form the leveling circuit. The modulator is set to minimum attenuation for frequencies less than 2 GHz generated by the synthesizer. If fitted, the optional step attenuator is situated between the matching resistor and the RF output connector. When the frequency counter is in use, an SP2T switch routes the counter input signal to the sampling gate instead of the coupled YTO signal. In the 6204 instruments, the microwave chassis and additional components are the generation of signals between 26.5 GHz and 46 GHz. And it goes on to talk about a doubler being used, a diode doubler and various other bits and bobs. So if we just go back to the section that talks about the limiter, it says the through path of the coupler is followed by a broadband modulator, which together with the resistive pick-off coupler, diode detector and control circuitry in the synthesizer form the leveling circuit. So what it's saying is, this is the resistive pick-off attenuator and that is the diode detector. So I'm wondering if the fault may be in the signal level leaving this and going to the synthesizer. And so if this is, for example, not giving a DC level output when it's sensing RF coming through here, that it could be that that's faulty. So the next experiment I'm going to do in part 4 is to put a voltmeter on this and see whether when I adjust the RF level here coming in, that the output level here goes up and down proportionally. Because if this is the sense output for the synthesizer to adjust the level of this in a locked loop as it describes in the functional description, then that may be where the fault be. So we'll check that out next and we'll come back in part 4. But what we'll do is we'll just have a quick look at the diagram just to get an overview of where things are. So again, this here is the RF section out, so that's that resistive pick-off. That's the diode detector, which is that separate module I've just pointed out, and I think that gets sampled back here. And if I can get the damn diagram to stop moving about, and it comes in just there. So yeah, we've got that signal going there, leveling amp. There's a switch there, and that obviously then goes off to external level input. That's interesting, that, because that's actually a socket on the back of the test set. So you could actually influence that by selecting in the software external level input and then adjust the thing up and down. But interestingly enough, we've got the signal diode detector, so we get DC level coming out, obviously proportional to whatever RF's been allowed through, which is fed back into the what is the leveling amp, and then it goes out the leveling amp through this switch, and then back as a DC control, which is where I'm feeding my voltage now to adjust the attenuator part. And we've also got a pin diode attenuator there, integral within the synthesizer unit, and an amplifier which is for the 10 megahertz to 2 gigahertz. So that's how it controls a 10 megs to 2 gigahertz RF signal, by a diode attenuator there. And it talks about the different switches there within the synthesizer block. These are the Yig tuned oscillators. Then we've got the bandpass filters, the pin switch. That's obviously from the synthesizer 10 meg to 2 gigahertz input. Then it comes out, goes through the coupler, and obviously that's a frequency counter input. It samples and gets fed back. And then we arrive in here. So some, you know, the description is good, but it doesn't really tell you much about how the leveling circuit works. But obviously that has got symbology in it, where it shows an attenuator symbol just there. So yeah, interesting. So what we'll do now, we'll see whether we've got a voltage coming out of here, and we'll see what happens. So I'll come back to you in the next part of the video, and we'll see what happens. Stay tuned for more in part 4. Thank you.